Welcome back. Okay, in this video, I'm going to show you how we remove heap. Now, recalling what the PowerPoint slides say, this binary tree that you're looking at in the slides is a heap. It is a minimum heap because the smallest value of a node is at the root, the top, and for each parent node, its child nodes have larger values. So in this case, as you can see, 2 is at the root, and its immediate children have values of 5 and 6, which are bigger than the parent's value. So that's a minimum heap. In addition, a heap must be a complete binary tree. For a complete binary tree, you must have all levels full except the last one. The last level can be full, but if the last level is not full, it's still a complete binary tree if the nodes on the last level are all on the left side. Now, this last statement makes it a little confusing. It said the last node of a heap is the rightmost node of maximum depth. Well, here's the last node. So, yeah, it's on the right side of the 5, but both the 9 and the 7 are on the left side of the level. So that's a complete binary tree. If the 7 were attached to the 6, we would not have a complete binary tree. If the 7 wasn't there at all, we would not have a complete binary tree either. Now, as I said, the way you remove a node from a heap is you always remove the root. So in the slide example, with a minimum heap, we're going to remove the 2. The procedure we're going to use then to get the tree to be complete, meaning have it a minimum tree again, is the first step is we're going to delete the root node and replace it with the last node, the rightmost node on the lowest level. In this case, that'd be the 7. So as you can see, the first step is the 2 is removed. The 7 winds up as the new root. And there's no root on that side of the 5. But now you have to reorder the heap to become a complete binary tree again. So to do that, you then pair the root node, the new root node, to its children. And in this case, for a minimum heap, we see which of the children is the smallest value. We compare it to the 5 and the 6. Well, the 5 is the smallest value, so we swap the 5 and the 7. And now we have a minimum heap again. This process is known as down heap or bubbling down. It's also called sink down. It's got several names. Okay, let's try and apply this to the example I'm using. Once again, I'm just going to use the list. I'm not going to draw a tree this time. So let's assume we have this list we're working with after inserting the 100 and inserting the 75. So our list looks like this. Put the numbers in. This is a maximum heap as opposed to a minimum heap. And I will put the index values at the bottom. All right. So we're going to start here in the remove root function. Here's what we're going to do. First, we check if we have an empty heap. If the length is 0, that means there's nothing in the heap. We return a none. The next thing we check is, well, is there only one element in the heap? So if the length is 1, there's only one value in the heap, so let's return that value. That removes the root. To do that, we're going to use a pop method. There is a built-in pop method for lists. What it does is it returns the value of the last element of the list. So if there's only one element, that's the only element, it gets returned via the pop method. Obviously, we have more than one element in our list, so we'll go to the next section. It says here, if the heap has 2 or more items, do the following. First, we're going to save the value at the root. We're going to put that into a variable. So we will have a variable named value. And that gets heap at index 0. That is the value 100. So that value goes in there. Next thing we're going to do is this. Change the value at the root to the value at the end, because that's the procedure for removing the root from a heap. So here we say heap bracket 0 is heap pop. The pop method will return the last element of the list, which is the 61. And then the first element will be overwritten by that. So what's going to happen is the 100 goes away and is replaced by the 61. The 61 also is removed from the list. There's nothing in that last slot anymore. We're going to ignore it. We also decrease the size by 1. Now what we're going to do is we're going to call this new method called sync down, and we're going to send it a parameter of 0. That is the index of 0 in this list. So let's look at what this sync down function is going to do. So here we're calling it, its parameter is index. So it's index, so index for now is 0. This is index right here. Index is 0. Also going to create a largest variable and set that equal to the value of index. Well, index is 0, so largest will also be set to 0. Now keep in mind, we're just going by index values here. You can clearly see that the value at index 0 is not the largest in the list, but that will change later. Now, we're in a loop that says while true. I usually don't like using a loop like this because usually that means you use a break or continue statement, which I also avoid. We're not going to use a break or continue statement. There's a return statement down here at the very end of the function, but we'll get to that later. So here we go into the loop. So the first thing we do is we get the indexes of the left and right children. For the get left child function and get right child function, those are up here. So the left child is 2 times index plus 1. Right child is 2 times index plus 2. Go back to here. So since index is currently 0, 2 times that plus 1 gives us a 1. So left is 1. This is left. And then right would be 2. 2 times 0 plus 2. So left is 1, right is 2. Left. Here's right. Yeah. All right. Now we have to check to see this. It says if left is a valid index and its value is greater than largest's, then set largest to left. So the first thing we check is left less than the length of the heap? Well, it is. And second is the value at index left. Left is 1, its value is 99. is that larger than the value of the largest index? Largest is 0, and it is. So guess what? It is. Therefore, largest is no longer there. Largest now moves to here. Okay, so largest becomes left. You must also check the right parent to see which node on that level is the biggest one. Right is 2. So if right is less than the length, which it is, and if right is greater than largest, well, now largest is now equal to index 1, and its value is 99. Right is index 2, its value is 75. So right is not bigger than the largest, so we don't set largest equal to right. So now largest has a new value. Now that that's done, it says, now see if largest is no longer equal to index, which it's not. Largest is now 1 in this case. Index is still 0. So if largest is not equal to index, swap those two values and set index to largest, okay? So guess what? What we're going to do is, that means the 99 and the 61 get swapped. 99 goes here. 61 goes there. And index is now equal to largest. So we no longer need left and right here. Index now goes here. Did not go to the else, so we go back to the start of the loop. Okay, while true. Let's keep going. Left is get the left child. We pass index. Index is 1. So 2 times 1 plus 1 would be the 3. Yep. So index is now 1. 2 times 1 is 2 plus 1 is 3. So left would go here. And right would go here. Left is now 3. Right is 4. This is equal to 1. All right. So if left is less than the length, which it is, and if left is bigger than largest, well, left's value is 58, largest is 61, not bigger. Now let's look at right. If right is less than the length, which it is, length is 5, and right is bigger than largest, oh, it is, so largest is now right. That means largest no longer is here, largest is here. And largest is not equal to index. Largest is 4, index is 1. So we're going to swap those two values. The 72 and the 61 get swapped. 72 goes there. 61 goes here. And index is now equal to largest. Well, index now becomes a 4. This. And we go back in the loop. Okay. So now we do left and right again, but largest, okay, no, index is now a 4. Well, guess what? Left child is 2 times 4 plus 1. That would be a 9. That's left. And right would be a 10. 2 times index plus 2. So that's 10. Those are going to be too big. So the first thing we check is left less than the length? No, it's not. That's false. And since we have an and, we don't do that. Similarly, we see if right is less than length. Nope. Length is 5, right is 10. So right's not less than length. And since we have an and, we don't do largest equals right either. And finally, we come down here, we see if largest is not equal to index. Well, the problem is largest is a 4 and index is also a 4. So largest is equal to index. That means this condition is false. So we go to the else, and that says return. That means we're out of the sync down function. And as you can see, this list is the same as that list. So that is our new heap, which is a complete binary tree. And that is how you remove the root from a binary tree. Once again, please forgive my lack of artistic experience. I really, really hope you find this helpful. I understand it's not the same as the textbook, but I felt we should do something a bit simpler than the textbook on this. So here's my best attempt. Please feel free to include your own comments about my videos in the discussions. Please keep them civil, but I am open to constructive criticism. But I sincerely hope you find these helpful. All right, if you have any questions, please send me an email at kmuldrow@lbcc.edu.